Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at projecting a particle at an angle, and we're going to use SUVAT to solve all sorts of different questions so we can answer questions from exercise 6c. So as I said, when we project a particle at an angle it will have an initial speed, and the way that we deal with those in SUVAT is we're going to be resolving that initial speed just like we did with forces. We're going to be splitting it up using a right angled triangle, resolving the different initial speeds, and then using SUVAT appropriately. Now remember, there are two different ways that we've got for solving these types of questions here. When you're working vertically, you're going to have to take into consideration that G, the force of gravity acting downwards, is always going to be applied. But horizontally, that speed, that initial speed, is not going to be changing. It's still going to have that initial speed no matter what it started with throughout the whole system. So your equation for that one is going to be slightly easier than the SUVAT one you're going to have to use for the vertical one. So let's get started in this question here then. A particle P is projected from a point O on a horizontal plane with speed 28 meters per second with an angle of elevation of 30 degrees. After projection, the particle moves freely under gravity until it strikes the plane at point A. Find the greatest height above the plane reached by P and the time of flight of P, and then the distance OA. So in our diagram here we're going to have a horizontal projection of 27 meters per second at an angle of 30 degrees, and it's going to get fired until it hits the ground again, so it's on one horizontal surface. When we're talking about plane here, we're not talking about a plane up in the air, a flying aeroplane. We're talking about the plane, the horizontal plane that we're working in here. So then, find the greatest height above the plane reached by P. So that's the greatest height above the horizontal here. Now let's think about what we could use here. Could we use the horizontal component to solve this, or the vertical component to solve this? I think the vertical component would be better here, because at that maximum point there, we remember that when we're looking at the velocity of it, the velocity at its maximum point is going to equal 0. So what we're going to do is we're going to work in the vertical component here, have an initial speed that we'll have resolved, and have a final speed of 0 where it reaches its maximum point. So the first thing therefore we need to do is to resolve our initial speed. Use a right angled triangle to do that, 30 degrees inside the triangle, 28 cos 30 on the adjacent side, 28 sin 30 on the opposite side. So therefore we're now going to say that the greatest height will be reached when the vertical velocity is 0, or in other words, as the particle stops moving and starts to move downwards. So resolving vertically and using SUVAT. So resolving our speeds up and down. Initial distance upwards is what we want to find out. So that's the greatest height above the plane. So S is our answer here. U is going to be 28 sin 30. Final speed vertically is 0. That's when it reaches its maximum point. And we also have minus 9.8 going downwards now. Why is it now suddenly going downwards? Well, because it's gravity, it's acting downwards. The acceleration for this particle here is going to be in the downward direction. And we're not interested in the time. So, given that we're not interested in the time, we're going to use a formula that links S, U, V and A together, and that's V squared equals U squared plus 2AS. So, substituting the values as appropriate, we're going to get a minus 19.6 here, so we'll add that onto the other side. So add the 19.6s onto the other side. This thing here will equal 196 eventually. So then divide by that and you'll get a distance there of 10 meters. Great, so the greatest height above the plane there is 10 meters. In the next case, find the time of flight of P. Well, in that case there, the time of flight of a particle will be when its vertical displacement is 0, i.e. it has the same height as it started with. So we're going to work with the vertical component here again, and we're going to set S equal to 0. So working vertically, S is 0, we want to find the time it takes for this whole flight to happen. So t is going to be our answer here. We're working vertically here, so the initial speed is going to be 28 sine 30. We're not interested in its final velocity. That would actually be minus 28 sine 30, but that's for another day. And acceleration downwards will be minus 9.8. And t is what we're looking to find. So we now need to block out v and find a formula that links all of these three things together. So therefore, s is equal to ut plus half at squared, and substitute in the values. Rearrange to work this out. Do a bit of factorising, so we've got 0 on one side and t's on both sides here, so we'll factorise out t, this t here, and one of the t's from this component here. So we're either going to get t as 0, well yeah, that kind of makes sense, at time 0 the displacement is 0, but for the other part we're going to have t is equal to, rearrange the equation, 2.9 seconds there. Okay, so there we are. So that's the time of flight. It's going to take 2.9 seconds to reach the other part on the horizontal plane. The distance from O to A now this is where we do need to work in the horizontal component, and that's much easier because we have no acceleration in the horizontal component. It's been projected by 28 cos 30, and it's going to stay at a velocity of 28 cos 30 throughout its whole journey. So therefore, we can use a slightly simplified formula here, which is just horizontal distance equals horizontal speed times time, or in other words, distance equals speed times time. So therefore, the distance that we actually want to work out is going to be the horizontal speed, 28 cos 30, times by time. We know that that total flight now is going to be 2.9 seconds. So do the calculation there, and you get 69 meters to two significant figures. So there we are. It's resolving the initial speed, and then deciding whether you need to work your equations in the vertical or the horizontal components there. That's the tricky part for this question, really. So another question then. A particle is projected from point O with a speed of v meters per second at an angle elevation of theta, where tan theta is 4/3. The point O is 42.5 meters above the horizontal plane. The particle strikes the plane 5 seconds after its projection. So effectively, the diagram that we're going to be drawing here is a particle that's been projected from a point O, that's 42.5 meters above the ground, with a velocity of v at an angle of theta degrees. And this is going to be its projection. It's effectively like if you were to throw a stone kind of upwardly direction off a bridge or off a building. It's going to travel upwards for a little bit, but most of its travelling time is going to be in the downward direction. So therefore, we need to now show that v is equal to 20 meters per second. Okay, so where are we going to start then? Is our first equation going to be in the vertical component or the horizontal component? Well, we have this vertical distance here, so that's probably going to be a clue that we're going to be working in the vertical component here. The first thing we'll need to do though is work out our sine and cos of theta from the information that tan theta is 4/3. So resolving our speeds first, we're going to have v cos theta and v sine theta first. And for the vertical component here, we're going to be using initial speed of v sine theta. Now we'll do a little triangle in the corner of our page then. Theta is going to be opposite over adjacent, so that's going to be 4 and 3 in those positions there. Pythagoras will tell you that 5 will go on the hypotenuse, so therefore sine will be opposite over hypotenuse, 4/3, and cos will be adjacent over hypotenuse, 3/5. So therefore sine is going to be 4/5 and cos is going to be 3/5. So let's get to it then. We now need to start working with suvat in the vertical component. So the ball starts with a distance 42.5 above the ground, So by the time it's gone from position O to position A, it's actually travelled a distance of minus 42.5 meters, because 42.5 meters is above the ground. If we want to get from O down to A, that's going to be a displacement downwards of 42.5. So that's why displacement here needs a negative 42.5 value. Initial speed is going to be upwardly v sine theta. Final speed we're not really interested in. Acceleration as well is also going to be downwards, minus 9.8. And we know that it's going to strike the ground 5 seconds later. So all that's left for us to do now is to ignore v and find an equation that links these four variables together. So s equals ut plus half at squared. Substitute the values into the formula. We know that sine theta is going to be 4/5, so when you do 4/5 times 5 you get 4, so that bit there could be simplified to 4v. Work out the other components separately, add your 122.5 onto the other side, and divide by 4, and you're going to get v as 20, which is exactly what we're looking for, so that's great. Okay, so we worked in the vertical components there. We used all the information from the SUVAT there. Make sure that you're setting one direction to be positive in your question. We set the upward direction to be positive, so therefore if it's gone from O down to A, then it's a displacement of minus 42.5. Upwardly direction for the initial speed, v sine theta. And acceleration is also going to be acting downwards, so that's why it needs a negative on it. So the difficult part for this question really was making sure that each component had the correct sign in front of it. And what you're going to do there to make sure that that is correct is you're going to be setting one direction equal to positive. We set in this question upward to equal positive. Now we need to work out the distance between O and A. We know the vertical component is 42.5. We now need to work out the horizontal component. So we're going to be using a bit of horizontal SUVAT here, effectively. We don't need to go through the whole SUVAT equation, because in fact we have no acceleration, we just have a constant speed in the horizontal direction. So we're effectively going to be using the formula distance equals speed times time. So horizontal distance will equal v times by cos theta, that's the horizontal speed. V we know is 20, cos theta we know is 3/5, so it's going to be 20 times 3/5 times 5, so that's 20 times 3, that's 60. So we know it's going to travel 60 meters in the horizontal component. So now the total distance from O to A, that's just a little bit of Pythagoras. So therefore it's going to be 74 meters to two significant figures. Okay, so moving on to a new question now. A particle is projected from a point O with speed 35 meters per second at an angle of elevation of 30 degrees. The particle moves freely under gravity. Find the length of time for which the particle is 15 meters or more above O. So start by drawing a diagram. Starts from the ground, projecting upwards with a speed of 35 meters per second at an angle of 30 degrees. And we want to find the amount of time it's above a value 15 meters above the ground. So what we're effectively going to do is find the time between this point here and this point here. We want to find the times that the particle is exactly 15 meters. There will be two of these. Hopefully we're going to get a quadratic from our SUVAT, and then we'll just work out the difference between the two times. So what we're going to be doing then is we're going to be using a bit of vertical SUVAT here to solve this equation. First things first though, we need to resolve the speeds. So it's going to be 35 cos 30 and 35 sine 30. 35 sine 30 is going to be the one that we're more interested in here. So let's resolve vertically and take upwards to be positive. So doing SUVAT for the vertical component here, we want to travel 15 meters upwards. Initial speed upwards is 35 sine 30. Final speed downwards we're not interested in. Acceleration is going to be going downwards, so we want minus 9.8 there. And we want to find the time at which it is exactly equal to 15 here. So we're going to hopefully get two values for t, and we'll get a quadratic in terms of t. So s equals ut plus half at squared will initially spring into mind. Substitute in all the values. We want a distance 15 above the horizontal, initial speed of 35 sine 30 times t, half of minus 9.8 times t squared. Simplify all of your terms there, take it all onto one side, and then use the quadratic formula, or you can use the quadratic equation solver in your calculators. You could do it all this way, or you could just bung it straight into your calculator. Right, and what your calculator will give you is 1.43 or 2.14. So therefore, that's the point. So 1.43 will be the time it takes to get to this point here, and 2.14 will be the time it takes to get to this point here. So therefore, the total time that it's above 15 meters will be the difference between these two times. So therefore, it's going to be 0.71 seconds above a distance 15 meters above the horizontal. Okay, so final question here then. A ball is struck by a racket at point A, which is 2 meters above the horizontal ground. Immediately after being struck, the ball has velocity 5i plus 8j meters per second, where I and j are horizontal and vertical components respectively. So that's much easier to work with. We've got the horizontal speed, we've got the vertical speed, no resolving necessary. After being struck, the ball travels freely under gravity until it strikes the ground at point B. Find the greatest height above the ground reached by the ball and the speed at which it reaches point B. And part C here is the angular velocity of the ball makes with the ground as it reaches point B. So let's draw a diagram then. It starts from 2 meters above the position, above the ground. It has a horizontal component of 5 meters per second and a vertical component of 8 meters per second. And we're interested in this point B here. But before that, to answer part A, we're interested in its greatest height above the ground. So to do that then, we're going to be resolving our speeds in the vertical direction then. So we're looking for the greatest height, and we know how to do that. We're looking for s when the velocity in the vertical direction is equal to 0. So then s is equal to the thing we want to find. Initial speed upwards is 8. Final speed at the point of greatest height will be 0, because that will be the point at which it starts to turn from upward speed to downward speed. A is the acceleration, that's always going to be directed down towards the ground with a value minus 9.8, and t we're not interested in. So therefore v squared equals u squared plus 2as, and therefore substituting in the values, rearranging it, and we get 64 divided by 19.6 is 3.3 meters to two significant figures. But that is the distance above the initial starting point. For our final answer here, we're going to need to add on the initial height of 2 meters to get the greatest height above the ground. So add 2 onto that, and you get 5.3 meters as your final answer here. Moving on to part B then, we're looking for the speed at which it strikes the ground at B. Now for the speed, we're going to need both the horizontal component and the vertical component. Now we already know the horizontal component, that's going to be 5. That doesn't change. 5 meters per second is going to be the constant speed that it's going to be travelling in that horizontal component. What we do need though is the vertical component. We need to know the velocity at which it strikes the ground at point B. So therefore, at point B, it's travelling 2 meters down, so we're going to resolve horizontally downwards. We want to find V effectively. We know it's going to travel a distance of 2 meters in the downward direction, and it's going to have acceleration downwards and initial speed upwards of 8. So therefore, we're going to do a little bit of suvat here. In this case, so we're going to set V equal to the positive direction, so we're going to set downwards as positive now. So you can choose which direction you set as positive. It probably will be easier to have downwards as positive here because we are looking for this speed v here. That would mean though that 8 the 8 meter direction that's going upwards now is now considered to be a -8 velocity because we're setting downwards to be our positive direction here. 2 here, we're going 2 meters in the downward direction. That would also then mean that the displacement is a positive value because we are setting positive to be downwards this time. Acceleration that's also going downwards will be 9.8, and t we're not really interested in. So once again, a formula that doesn't include t is v squared equals u squared plus 2as. So therefore v squared equals u squared plus 2as, substitute the numbers in, and we're going to see that v squared will equal -8 squared plus 2 times 9.8 times by 2, and work out the right hand side. We're going to get v squared is 103.2. We can work out v by square rooting that to 10.2. Okay, so that's going to be the velocity going downwards. We're looking for the total speed though that the ball reaches point B at. So remember, speed is going to be the total value of the two velocity vectors. We're going to have 5 going to the right, and we're going to have 10.2 going downwards. So now all we need to do is a little bit of Pythagoras theorem with those two values there. We're going to have 5 going to the right, 10.2 going downwards. The total speed then will be the Pythagoras value in that hypotenuse length. So it's going to be effectively 11 meters per second squared going in this direction here. We also need to know the angular velocity of the ball makes between the ground and the ball's projection. So we can now use a bit of a tan calculation to work that out as well. We're interested in this angle round from here to here, the angle that makes with the angle of velocity the ball makes with the ground. Yep. So we could work out this theta angle here if you wish to do that. So it's going to be opposite over adjacent. That's going to be 0.49 is the value for tan. So theta is 26.2. But the actual answer we're looking for is going to be this angle round from here to here. So 90 minus that, and we get 63.8. You could have reoriented your diagram to have the 5 down here and the 10.2 here. That would have been exactly the same thing there. So you'd have had tan minus 1 of 10.2 over 5. Either way round, you're going to get an angle of 63.8 as the angle that the ball will make with the ground. Right, so a lot of tough questions there. It was a tough section. Do pause the video and have a go at this question before we move on to more questions in exercise 6C though. So pause the video and try this question out. Okay, so let's have a go at this question then. A particle is projected from point O on a horizontal plane with a speed of 20 meters per second at an angle of elevation 45 degrees. The particle moves freely under gravity until it strikes the ground at point X. Find the greatest height above the plane reached by the particle and the distance OX. So to draw a diagram of what's happened here, we have our horizontal plane and our particle has been projected like this. X is over here, O is over here, and we have an initial speed of 20 meters per second. We're first going to need to resolve this, so it's going to be 20 cos 45 in the horizontal component and 20 sine 45 in the vertical component. So the first thing we need to do is find the greatest height here, and if you remember how to do that, it's going to be resolving our suvat speeds and accelerations in the vertical components until we get a final speed at the top here. That final speed at the top there will be 0, so v in our suvat will be 0. Initial speed will be 20 sine 45. If you actually work that out, that's going to be 10 root 2. S, that's what we're interested in finding, so we'll leave that in there. And acceleration is going to be minus g, the force, so the acceleration downwards due to gravity. So let's put this into the equation. V squared equals u squared plus 2as. V squared, that's 0. U squared is going to be 100 times 2, so that's 200. And it's going to be plus 2 times minus g times by s. So cancel out the 2's there. So it's going to be s equals 100. Once we've added that onto the other side and divided by g, it's going to be 100 over g, which is going to be 100 divided by 9.8, which is 10.2 roughly. So 10.2 meters above the horizontal will be its greatest height. Okay, the next thing we need to do then is work out the distance from O to X. Now we need to do this in 2 stages. We need to work out the time that it's going to take to travel from O to X, and then we can do a bit of distance equals speed times time for the horizontal component. So we are still going to be working in the vertical component here, but for where we have a displacement in the vertical direction of 0. So we want it to travel a distance 0 in the vertical component. The initial speed in that vertical component was 10 root 2. V we're not interested in. A was minus g, and t is what we are interested in. So s equals ut plus half at squared. And let's substitute in the numbers. So it's going to be 0 equals 10 root 2 times t. Plus a half, so let's do it as minus because it's going to be a minus g. Half of g is 4.9, and that's going to be t squared. So then factorize out the value for t, so that's going to be t times 10 root 2 minus 4.9t. So t is therefore either going to be 0, well yeah, that makes sense. T, the starting point will obviously have a displacement of 0, but also t could equal, let's rearrange this thing inside the brackets to find out what t could equal. I think it would be 10 root 2 divided by 4.9, and when we do that, divide by 4.9, we're going to get 2.08. So it has a travelling time of 2.08. Let's now use that in horizontal distance equals speed times time. So the distance horizontally is going to equal the speed horizontally, which is 20 cos 45, that is 10 root 2 as well, times by the answer value for the time, 2.08, and on your calculator you'll obviously be using your answer button at this point, so times 10 times root 2, and we get a total distance there of 29 meters to 2 significant figures. So there we are, that's the answer to this question here then. Have a go at plenty of the questions from exercise 6c. This is a difficult chapter, one where you're having to use 2 types of equations, the vertical component of SUVAT and the horizontal distance equals speed times time sort of equation there. So yeah, have lots of practice at this. We're going to use algebra in exercise 6d, so the more familiar you can get with this with numerical values will be for your own benefit. So take some time to have a go through the problem solving ones, the exam style questions, and thanks very much for watching.